Namaste. Welcome to the lecture series on the subject Basic Thermodynamics, Module 3, Part 2, Entropy, Lecture number 15. Myself, Dr. N. Satish Kumar, Associate Professor of Mechanical Engineering, Canara Engineering College, Benjanapadam, Bantwal. The contents for this topic is again the continuation of the numericals on entropy calculations. So let us take this numerical. Calculate the entropy change of the universe as a result of the following process. So a copper block of mass 0.6 kg and specific heat 150 joules per Kelvin at 100 degrees Celsius is placed in a lake at 80 degrees Celsius, and two such blocks at 100 degrees Celsius and 0 degrees Celsius are joined together. Okay, now two problems are there. One is a copper block of mass 0.6 kg, that is the mass, copper block, of specific heat 150. Now look at the unit of specific heat. It is given joules per Kelvin. That means here kg is not there. That means it's already multiplied by mass. So this you have to take it to m into c. Very, very important. By looking at the unit joules per Kelvin, so it is called as thermal capacity, m into c. Okay, so that is 150, though it is mentioned as specific heat, but it's not specific heat. Then you can ask me, can we find out to C specific heat of copper? Yes, since the mass is given 0.6 kg, so you can divide this by 0.6 and you can find out Cc also, but it's not required because the formula itself is having mass into specific heat, so directly you can substitute 150. Okay, that is the first question. Now here the first question, the very important part to be noted is here that block is placed in lake. Now lake you have to consider it as a reservoir, very important. Lake should be considered as a reservoir whose temperature doesn't change even if that block is placed in lake. Whereas in the second question is different. Two copper blocks are there, both are having same mass 0.6 kg, but one is at 100 degrees Celsius and one is at 0 degrees Celsius, and they are joined together so that heat transfer takes place between them and they attain the equilibrium temperature. Okay. So this is given m is equal to 0.6 kg, m into Cc is 150 joules per Kelvin. Okay, it is no need to convert into kilojoules. Okay, even if you convert to kilojoules, this kg should not be there, it's a print mistake. Okay, so let us substitute use the, neglect this all of you. Okay, please. And copper temperature is 100 degrees Celsius, which is nothing but 373 Kelvin. Lake temperature is 8 degrees Celsius, which is nothing but 281 Kelvin. Okay. Now delta S universe is equal to delta S copper block plus delta S lake. So here first problem actually, this is case 1. Here delta S universe is equal to delta S of copper block plus delta S of lake. Okay. So when hot copper block is put into lake, the block shall cool down to the lake temperature, since lake is being treated as the sink. So the initial temperature of the copper block is 100 degrees Celsius and final temperature will be the temperature of the lake. That is, I think it is 8 degree Celsius. Okay. So here delta S copper block whose temperature is changing is nothing but mass into specific heat, and then directly you can write, because no need to write the formula for integration at all, directly you can write ln TL, that is final temperature, which is the lake temperature, 8 degrees Celsius TL, and initial temperature of the copper 100 degrees Celsius. So substitute in Kelvin. So this is 281 Kelvin, this is 3873 Kelvin, and MC into Cc I told you in the previous slide. So that together should be taken as 150. It is in joules per Kelvin. Okay. So you will get delta S copper block is minus 42.4835 joules. You see, joules. Okay, per Kelvin. The same unit of this m into Cc will come here. Now heat lost by the copper block is equal to heat gained by the lake. Okay, so m into Cc into Tc minus TL, heat gained by the lake. Okay, is nothing but heat lost by the copper. So this is the formula is for the heat lost by the copper, because lake temperature doesn't change, so you can't use that formula. Okay, So m into Cc for copper into copper temperature 100 degrees Celsius minus lake temperature 8 degrees Celsius. So that is the heat lost by the copper. Actually it is formula for heat lost by the copper, but it is equal to heat gained by the lake. So you will get it around 13,000 joules. Okay, here. So delta S lake is equal to Q. Now this becomes Q for the lake. Okay, heat gained by the lake. Okay, it's positive. So that is what is taken positive here. Okay, divided by at what temperature the heat was absorbed? Lake temperature 8 degrees Celsius or 281 Kelvin. So you will get it as 49.11 joules per Kelvin. You see, whenever the reservoir comes into picture, like lake, so there the entropy change is directly Q by T. Remember this. I did this in one of the problems earlier also, one of the previous lectures. Only when the temperature changes, so you have to use the integration formula. Here lake temperature doesn't change, so Q by T, but the Q directly you can't find out for the lake because lake temperature doesn't change. So you have to find out that whatever it has absorbed, that is given by the copper block. So what is given by the copper block? mCc into Tc minus Tl, which comes around 13,800 joules. So this is very, very important when you solve this kind of problems. Now delta S universe. For the first case, delta S copper block plus delta S lake, you will get it as 6.63 joules per Kelvin. So it has to be positive for sure. Okay. Now case 2, mass is 0.6 kg, but it doesn't make any sense since mCc is given. So mC1, mC2 is 150 joules per Kelvin. Once again this term is not required. Okay, neglect this. And Tc1, Tc2. Now here Tc2, both are copper block. One copper block is at 100 degrees Celsius, other copper block is at 0 degrees Celsius. This is very important. Okay, I have to mention this here. Now it is not the lake. Two copper blocks are joined together. Okay, so they are connected. Now just explanation, as all of you know, when two blocks, one at high temperature and one low temperature is brought together, so they attain the equilibrium temperature. Earlier I used the symbol Tf. Now I am using the symbol Tm. If you want, you can use the Tf only. So Tf will be less than Tc1 and greater than Tc2. That means it is less than 100 degrees Celsius, but it is greater than 0 degree Celsius. Okay. So this is the formula, as all of you know. Heat lost by the block 1 is equal to heat gained by the block 2. So let me not elaborate on that. So you can find out Tf. Once again, you know how to use this formula. Okay. So since here mC1 and mC2 are equal, so it just becomes T1 plus T2 by 2. You see, when m or is the same, C also same, that mC product is also same for both the things. So then it becomes just, you see, this term gets cancelled, this term gets cancelled, this term gets cancelled, this term gets cancelled. So numerator Tc1 plus Tc2, denominator 1 plus 1 is 2. So denominator is 1 plus 1. Okay, that is 2. So it's just average temperature. That means 0 and 100 both are of same mass, means it should be 50 degree. Directly I can say now itself, without calculation I can tell that the answer is 50 degrees Celsius. So 323 Kelvin means what? It is 50 degrees Celsius only. This is same mass, same specificate, one is at 100, one is at 0, it will be the exactly center value, 50 degrees Celsius average. But if the mass is different, specificity is different, if the substance or fluids or bodies are different specificates, so then you will get the different answer. Okay, but be careful. So delta S block 1, so its temperature has decreased from Tc1 to Tm. You can see, I think no need to elaborate on this formula again. So you should get a negative answer for the first block because its temperature is reduced from 100 to 50, whereas for the second block its temperature is increased from 0 to 50. That is initially Tc2 and finally 50. Okay, Tm. So 323 by 273 for Ln term, you should get positive because here the ratio is more than 1, greater than 1. If this ratio is greater than 1, you will get positive. If this ratio is less than 1, as you can see here, so the quantity will be negative. So for the substance which is losing its heat, whose temperature has decreased, so it will give negative value. Okay, and universe, it is 3.638 joules per Kelvin. Okay. Now heat engine is supplied with the 270 kilojoules of heat at a constant fixed temperature of 283 degrees Celsius, and the heat rejection takes place at 5 degrees Celsius. The following results were reported. This similar problem I solved in fact during the theory lecture. Okay, still let me complete this also. So first case 208 kilojoules of heat is rejected, second case 139 kilojoules, third case 70 kilojoules. Classify which of the results report a reversible cycle, irreversible cycle and impossible cycle. So as all of you know, this you can solve, but still let me show you the solutions. So these are the three cases of the heat engine. Case 1, so it is observing, you see source temperature is same for all, okay, 556 Kelvin, 556 for all the three cases, and sink temperature is also same, and all the three heat engines should absorb the same amount of heat also, that is 270, 270 and 270. Only thing is the rejection quantities are different, 208, 139 and 70. So one of the engine is reversible, one is irreversible and one is impossible. So let us check that. Case 1, summation or cyclic integral of del Q by T. So it is absorbing 278 from 556 Kelvin, rejecting 208 to 278 Kelvin. So the answer is minus 0.2482. So summation of del Q by T is less than 0. It is irreversible engine. Okay, whenever you get negative, it is irreversible. Case 2, I think you can recall that diagram. So wherein 139 is rejected, the rest of the quantities are same, and you will get exactly 0, the answer. So this is a reversible engine, because only for reversible engine cyclic integral of del Q by T is 0. Now the case 3, the rejection quantity changes to 70, means less is rejected, means it indicates that more is converted into work, which is not possible usually. So here this is greater than 0, which is positive, so this is impossible. Okay, with this I conclude this module 3 of this lecture series, and I will continue with the next module in the coming lectures. Okay, thank you. Also I'll try to solve a few more problems from the work and heat, first law, second law and entropy, maybe one each additional lectures, and I may upload that also for your understanding. Thank you.